So a Norman window has a semicircle at the top of a rectangle. And the diameter of the semicircle equals the width of the rectangle. We want the area of the largest possible window given a perimeter of 50 feet. All right, so first step on any problem like this is sketch it out. So I got a rectangle. And then on top of the rectangle, we have a semicircle. Something like that. Put a dotted line here. So that's the diameter, and they say the diameter and the width are the same thing. And then we have this height right here. So this is the window they said, right? Semicircular top, rectangle. And rather than the diameter, we would prefer the radius. So my radius here would just be whatever the width is divided by 2. And remember, we want to minimize variables. So right now, it looks like we have a diameter, a width, a height, a radius, way too many. We got to get it down to a couple of variables. And we ultimately want the area of this. So area is in 2 parts, right? Area of the rectangle, which is the width times the height. And then the area of the semicircle, which would be 1/2 pi r squared. And based on the note that the diameter of the semicircle is the width of the rectangle, right? Normally radius is diameter over 2, but here we're going to consider it width over 2 because we don't want to have so many variables. So we got to clean this up. So we have width times height plus 1/2 pi. And anytime we do a substitution, use parentheses to be safe. We get a W over 2 there. All right, so cleaning that up, what do we get? We still have WH out front. And then we have 1/2, we have a 2 squared on the bottom, 4 times 2 is 8. So we get pi over 8 W squared when we clean up this here. So that's my formula for the area. And problem with this formula is there are too many variables, right? Area is too many variables. Area is a variable, W is a variable, H is a variable. You need to get it down to a single variable. We still haven't used the perimeter, so that's what we're going to use to whittle down the number of variables here. All right, so first step, find an equation. Second step, do some kind of variable substitution with the information. Perimeter is 50 feet. So what's the perimeter? Well, I have a semicircle as part of my perimeter. Let's highlight that. Okay, so perimeter. We have 1/2 of a circle, which is 1/2 of 2 pi times the radius. And then coming around this thing, we have a height and another height. So there's 2 heights in the perimeter and a width. Okay, so plus 2 heights and a width. So there's my perimeter. And let's clean up some more variables here. We don't need R, right? Because we know R is W over 2. And we can clean up the 1/2 times 2. So 1/2 times 2 is 1, times pi is pi. Instead of an R we know is the width over 2. Plus 2H plus W, and that has to be 50. So we can use this right here to get rid of W or H. And ultimately we want the area, so it really doesn't matter whether we get rid of W or H, which looks easier. And I'm thinking it's going to be easier probably to solve for H. We got to clean this up a little more. So pi times W over 2, we could write that as pi over 2 W, and then we have plus another W, put them in order, and then plus the 2H, that's equal to 50. And we could factor this W here, but I think I'm just going to subtract it to the other side. So I'm going to get 2H equals 50. Maybe W would be the better thing to solve for. I don't think it matters. We'll see. Minus pi over 2W minus W. Oops. All right, so we just subtracted this and this over to the other side, divide everything by 2. And we get H is equal to all of this. Switch color there, put it in blue. Come on, blue, where are you? There we go. So 25 minus, that would be a pi over 4W minus, I'll just leave that as W, so I forgot my W over 2. And again, we could factor the W, but I don't think that's going to make things any neater algebraically. This is what H is equal to. So I can use that up here to get the H out of the equation and have it just be area versus width. All right, so putting all this together, we're going to substitute our perimeter into our area. So area is equal to W times, and we're going to drop in this for H, right? Parentheses to be safe, 25 minus pi over 4W minus W over 2. And then we have our plus pi over 8 W squared. So W times H plus pi over 8 W squared, that looks good. Distribute the W, clean this up before the derivative. All right, what do we get? We get 25W minus pi over 4 W squared minus W times W, another W squared over 2, plus our pi over 8 W squared. And maybe it's time to factor out that W squared and combine like terms there. Why not? All right, so take this to a new page where we have some more room. We've got the area equals 25W minus pi over 4 W squared minus W squared over 2 plus pi over 8 W squared. Did I copy that right? Looks like it. All right, and then we're going to clean up this right here. So there's a W squared in each term there, so we can pull out the W squared. Oops, squared. We got the 25W out front. And then I'm going to write it as, should we pull out a minus also? If we pull out the minus, that changes the sign of everything here. So that leaves pi over 4, right? We pulled out the minus, pulling out the minus over 2. So that's going to be a plus 1/2. And then we're factoring a minus, so that would be a minus pi over 8. Again, because that minus is now out front, all the signs change. Pi over 4 minus pi over 8, that cleans up a little bit more. That is pi over 8. So we get 25W minus W squared times pi over 8 plus 1/2. And I don't see the point in cleaning that up further. Guess we could have a common denominator of 8. Sure, why not? 25W minus W squared times, so we'd have to multiply by 4 over 4 here to get a common denominator of 8. So that's going to give us pi plus 4 over 8 as the constant. All right, so remember, strategy here, back up a sec. First, we have to come up with an equation for what we're trying to optimize. We're trying to find the largest possible area. So area is my focus. My area equation had too many variables. So I had to do what I could in the geometry and with the given information here to whittle those variables down. once we get it whittled down to a function of a single variable, then we're ready to take the derivative. So I want to know what's the derivative of the area with respect to this variable W. So derivative of 25W is 25 minus derivative of W squared is 2W, and the pi plus 4 over 8 is just a constant. It just gets carried along. And the 2 over 8 cleans up a little bit. So we get 25 minus W times pi plus 4 over 4. And set it equal to 0. Find a critical value. Add the 25, or I guess subtract the 25 to the other side. So we get negative W equals negative 25. And then we're going to have to divide by this and the negative. So that W equals negative over negative is a positive 25. And I guess instead of dividing by this, we'll multiply by the reciprocal. 4 over pi plus 4. So 100 over pi plus 4 is the width that should give us the maximum area. So this is the width to find the max area. And then we'll check it graphically to see if it works out. So we need an approximation of that. Whip that out on a calculator on the side. If I could type, I get it's about 14.0025-ish. All right, so then we got to backtrack. So we have a width. So let's put it all together. So our width is 100 divided by pi plus 4, which appears to be about 14.0025. To find the area, we need the height also, and then we can get the area. Oh, actually, we don't even need the height because we whittled that out of the equation. We can just go straight to the area. But I'm always curious about what all the dimensions are. But let's first get the area. Our area equation is, we got a cleaned up version here or here. We can just plug in W into that. So 25W minus W squared is our formula times pi plus 4 over 8. So I'm just going to plug this W in here. Calculator time. So here's that value of W, and call it W. And I'm going to enter this as a function, so I'm going to call it A of X. And it is 25X minus X squared times pi plus, oops, I need my division before the plus. Double check I typed that correctly. And I don't care about the graph yet, but we'll look at that in a minute. And we think if we plug in that value of W, we'll get the maximum area. So according to the calculator, the maximum area is about 175.031. So this is about 175.031. So let's see if that looks reasonable on the graph of this function right here. So I entered that as a function of X on my calculator here. And I should see that the point that's the highest here, right? This is a quadratic. The highest point should be the point that's about 14,175. So if we adjust the window to see that, so let's go out beyond 14. So maybe we'll go out to X equals 20, and then Y, let's go up to like 200. And then the maximum point should be right here at the top, which should be that 14.002. There we go, 175, we nailed it. Now, this is only correct, right? That point Desmos gives me if all of that other work I did was right. So let's back up and double check that. All right, other work. All right, and we had to do quite a bit of work to get to this point right here. So the question, is this actually the correct area formula in terms of the width? You got to go rethink what we did. All right, so they told us a Norman window is this semicircle and a rectangle. Cool. They told me the diameter and the width are the same. Diameter equals width here. Got that. And then for circles, we need the radius. So the radius is normally half the diameter, which in this case is half the width. So anytime we need a radius, we're going to throw in half the width, width over 2, which we did. So at first, our area had 1, 2, 3 variables, too many. We got rid of the R just through the geometry of the problem. But then we were still stuck with that H there. So the only way to whittle down that is to have another constraint, another way to connect variables. And that was where the perimeter came in. So we found the perimeter, used that to solve for H. And then from there, we just solved for H, plugged it in and did the cleanup. Now you might ask, well, why didn't I solve for W at the perimeter? We totally could have done that. We could have solved for W. In this case, instead of area as a function of width, we would have area as a function of height. And the formula would have been different, but it would lead to the same area in the end. So if you're bored later, you could, instead of solving this equation right here for the width, solve it for the height. You'll still get the right area in the end, right? But we'd have to pick up from this step and then redo all of this work here. So if this were on a test and you wanted to be sure it was right, I might come back here if I had some extra time and solve for H, complete the process again and see if I got the same height or same area. If you did, then you must be doing the right thing. If they didn't match, then one of them has a mistake in it. Question is which one? Clean piece of paper, start over.